Thank you. Thank you, Jianfeng, and thanks to all the organizers for putting together this workshop. It looks great, and I'm very happy to be able to speak in it. I'm going to talk a fairly high-level talk about a number of publications I've been involved in, or publications are soon coming, related to learning solution operators for partial differential equations. I'll show you some methodology, some applications, and some theory. And also, I think what I will describe is perhaps points forward to the work that Sid Misher and Gita Petoniuk will be describing in their talk, where they will study in more detail some of the interesting analytical challenges around this general area. So I welcome questions as we go along. I probably won't be able to read the chat, but if you prefer to put things in the chat, perhaps Jianfeng can convey them to me. But otherwise, I'm very happy if you just interrupt and ask me questions. And I'm planning on 40 minutes. Is that correct, Jianfeng?
Yes.
Okay. So I'll start by describing the problem setting. I'm going to describe two methodologies. One I'll call the kernel network approach, which I will try and relate to standard neural networks. And within this context, I'll describe applications to fluid mechanics. And then the second broad class of methods I'll describe are based on model reduction. And I'll explain that methodology, some theory, and application to a problem in homogenization from plasticity. And then at the end, I'll describe some theoretical work concerned with trying to understand a little bit more nuanced questions about how difficult or less difficult certain classes of problems are by studying the learning of linear operators between Banach spaces and trying to distinguish between unbounded, bounded, and compact operators from the point of view of their learnability. Okay, and I'm happy to make the slides available, and you can follow up on references that way. So the setting that I'm going to be working in this talk is this one. I'm interested in learning an operator or a map between function spaces, and we'll call that psi dagger. So that's our unknown function that we wish to recover from data. And specifically, X and Y for this talk will be function spaces. More generally, this idea is applied to X and Y being separable Banach spaces, but you should think for this talk of X and Y as being spaces of functions over a domain D in Rn, in Rd. And we're given data, pairs Xn, Yn, and just for simplicity, I will at the moment just assume that these are given exactly as described here. The Xn from IID from a probability measure mu on the Banach space X, and the Yn being essentially found through the push forward of mu under psi dagger. So our access to psi dagger is through the push forward, information about samples from the push forward measure, coupled to samples from the input measure mu. And then what I'm going to be doing is seeking approximation for a class of operators, which I'll call psi, parameterized by theta, mapping again X into Y. And I'll assume that uppercase theta is a subset of Rp, so P is the number of parameters. The objective is to design this class, operator class psi, in such a way that by choosing a parameter theta star from theta, we can obtain a good approximation to psi dagger, where psi dagger is known to us through this data. And the one philosophical point that underlies everything I'll describe in the talk here, but it's an idea that applies more widely throughout scientific computing, is that it's beneficial, I believe, in this context and in many others, to conceptualize the algorithm, which in this case is designing an architecture, to do that on function space before you discretize the function spaces. And the reason why that's a useful way, an important way of thinking, in my opinion, is that if you first discretize and then use standard methods, in this case, neural network architectures, many of them will not be well adapted to the function space setting. So if, in contrast, you postpone discretization until the last minute and first of all, conceptualize the algorithm as an architecture in this case, between spaces of functions, you narrow yourself down to a class of architectures which behave well once you discretize. So it's, I think, a persuasive way of thinking about scientific computing, and these ideas have been relevant in optimization and Monte Carlo Markov chain. And I want to show you how this way of thinking applies in the context of supervised learning for operators between Banach spaces. Okay, so that's the basic philosophy. All right, so let me describe then. So in the talk, there will be two classes of networks, one what I call kernel networks and the other which I refer to as model reduction. So let's start by talking about the kernel network approach. This is joint work with a number of people. Let me just tell you who they are. Zhongyi Li is a PhD student in computer science at Caltech. Nick Kavatsky is a computer science, is an applied mathematician, also PhD student at Caltech. Kamyar is a professor at Purdue. Bergader is a postdoc in material science at Caltech. Kaushik also. And Anima is a professor in computer science. So we have a number of papers related to what I'll call the neural operator approach, and I'll now describe to you what that is by viewing it as a conceptual generalization of classical neural networks. Okay, so the classical neural network, so here I'm just going to look at mappings between Euclidean spaces. They take this form. So this is a mapping from Rm to Rr, and I just write this in this fairly standard form of a deep neural network, starting with a linear transformation, iterate the composition of linear transformations with a ReLU function or other such function, and then at the end another linear transformation. And the parameters of the network are made up of all of these linear transformations or affine transformations. So the matrices, the A, uppercase A's, and the vectors B's. All right, so now I want to generalize this to a setting in which the input X is a function and the output psi is a function. So I'm going to look at the setting where the input space X is a subset of the functions from domain D in Rn into Rm, and Y is a subset of functions, for simplicity, over the same domain, D in Rn into Rr. And I'm going to make a neural network which looks like the deep neural network I've just shown you, but I think it's helpful to think in terms of local and non-local operators, or what I call here pointwise operators and non-local operators. And these are the analogs of the matrices and vectors which you saw in the finite dimensional setting on the previous slide. So I'm going to start with a pointwise operation, which just involves taking the function x. So x is a function in uppercase X. Z denotes the independent variable, so Z varies in the domain D. So this is just a pointwise operation in which at each point Z, we just apply a linear transformation defined by matrix A0 and vector B0, an affine transformation. And then we iterate as before with the following form, a pointwise operation, think of a ReLU or other such monotonic function. We have pointwise operation here and here, but we have a non-local operator, which I'm writing through an integral kernel, kappa sub L. So this is an integral kernel which acts on VL minus 1, and with addition of this linear transformation and then application of the ReLU gives us a function VL. So this maps VL minus 1 to VL, we iterate it, and then we end with another pointwise linear transformation. The parameters of this neural network are again the matrices A, the vectors B, and now additionally this kernel KL. So KL is itself now a function that maps R to N, because it has two variables in the input space, maps R to N into matrices. And this we also parameterize as a neural network. So this is a finite dimensional function, so we can parameterize it as a finite dimensional neural network. And as a consequence, we have an architecture on function space that maps functions X in X into functions in Y, and is parameterized by the A's and the B's and the parameters of the kernel KL. And then here in this bottom panel, I'm just emphasizing that this is a mixture of pointwise operations, or Nimitsky operators, if you're familiar with that notation, and a non-local operator, which is here expressed as an integral operator. So again, I welcome questions if there are any. Now is a good point, because I would like you to understand this architecture, because I'm going to show you some consequences of it over the next few slides. Okay, continue. I see there's something in the chat. If let me, okay, Jan.
Don't worry, just monitor.
All right. So let me say a little bit about computational efficiency. So I could say more on this, but making this architecture efficient is non-trivial in general because of the non-local nature of this operation here. For this talk, I'm going to talk mainly about using Fourier representation of the kernel, and then one can speed up considerably the application of the non-local operator using FFT. But there are other ways to do this, and I'm happy to discuss those in detail with anyone that's interested. So this is not the only way that we speed things up, but this is one such method, and it's good to think of that. So if one writes uses the convolutional structure of Fourier transform, and then works in Fourier space, and the parameters theta are a tensor which maps the coefficients of the Fourier transform of V into new Fourier coefficients, which are then inverted.
So can I have a question?
Yes.
So in the discrete case, you didn't have anything like a non-local operator?
No, that's right. I mean, I guess I guess one has to think about what one means by locality in the finite dimensional case. In some sense, matrices are already non-local if you're on RM, because
this is what confuses me.
So everything is non-local. It's just that the issue is not quite so clearly distinct. Whereas here, these ALs really act pointwise, so they are just finite dimensional matrices which act on the function VL minus 1 evaluated at Z. So it's simply VL minus 1 at Z is simply a vector. So this operation really is pointwise. Likewise, this is just a shift by a pointwise vector, the same one at every point Z in space, whereas this is genuinely non-local. And likewise, the ReLU or other such monotonically increasing function is applied as an Nimitsky operator, so it is also pointwise. So the only non-local operation is this. Did I answer the right question?
Yeah.
Thank you. It's a very good question. Okay, so
so Andrew, maybe this is going to be for later, but just a question for also how should I be thinking about the setup. So the Z and S, you said that they are like parameters in dimension n here. So yeah. How should I think about n? Should I think it as like 2, 3, or should I think it as like a high dimensional?
Oh, thank you. That's a really good question. I think looking at this general area more broadly, there have been significant uses of neural network ideas to solve partial differential equations in high dimension, where n itself would be high. In that case, the solutions are not being sought as an operator. It's just using the fact that the solutions themselves vary over a very high dimensional space. So n is large. here, the high dimensionality comes not because n is large. At the moment, you think of n as being 2 or 3, so physical problems. And the high dimensionality comes from the fact that I'm trying to learn the operator, which takes, say, the initial condition of a partial differential equation into its solution at a later time. Now, these two strands of high dimensional PDEs, where n is large, and learning operators, they too could come together, and then the problem will be doubly difficult through the infinite dimensional nature of the function space and the high dimensional nature of n. But for this talk, think of n as small, and the high dimensional nature coming from the fact that we're seeking dependence over the whole of the function space x, equipped with some measure.
Understood. Yeah, makes sense. Thank you.
Thank you. Okay, so a question that is natural to ask is the one that has been answered for standard neural networks in finite dimensions, which is the question of universal approximation. And Sid, who is giving the next talk, is one of the leading experts on this question, together with his co-worker Samuel Landthaler, who is a PhD student in Sid's group, and also Nick Kavatsky, who is a PhD student at Caltech. So there are a number of papers arising in this area. I'm not going to go into them in detail, but I would just draw your attention to 3 papers here. One by Kavatsky, Landthaler, and Mishra, which looks at universal approximation property of the Fourier neural operator. There's another competing methodology known as deep O-nets, and Samuel, Sid, and George Karniadakis, who is George being one of the originators of this method, have also proved universal approximation results for this operator approximator. And Nick Kavatsky, in a paper that will soon appear, has further analysis of this general methodology beyond the Fourier case and into more general kernels of the type that I showed you a few moments ago. So the point of this slide is to say that working within this class of neural networks that map between spaces of functions, there is a universal approximation. And then deeper questions about the cost of doing this in terms of size of the network, evaluation of the network, and so forth, amount of data. Those are questions which are going to need further analysis going forward, and some of which is touched on in the work of Sid Mishra and Sam Landthaler.
Yeah, maybe it's a good time to interrupt with this question. So Changdu was asking whether you work with something in between, like kernel with compact support, in between Fourier and complete local operators? Yes,
that's a very good question. So the answer is yes. So when we are not doing the Fourier neural simplification that I described to you, we are indeed working with compact support. So if you can think of multiplying this kernel by an indicator function of a set to restrict the support, that doesn't really beat the n-squared curse of dimensionality, but it certainly changes the constants. We also have used multipole type ideas to speed up this part of the approximation, and Nystrom ideas to look at connections between graphs at different levels of resolution. So I can point to papers where we've looked at that in detail. It won't play a big role in this talk, but that is a very important direction. Thank you. Important for making the method tractable. All right, so let me just show you quickly an example. So this comes back to Joan's question a few moments ago. So just to set the scene, I'm going to look here at solving Berger's equation. So this is a viscous Berger's equation with smallish viscosity. And what we're interested in is the operator that takes the initial condition to the solution at time 1. And what the potential benefit of what we're doing here is that we can speed up the computation. This is a trivial equation to solve, but as you'll see later with the Navier-Stokes equation in a few moments, we get speed up by many orders of magnitude over solving the partial differential equation by a numerical method. And that means that when one performs tasks that involve repeated evaluation of the solution operator, such as uncertainty quantification or design optimization, things become tractable which were not tractable before. So for this problem, mapping the initial condition to solution at time 1, I'm going to measure the relative error in the Bochner norm. So relative because we have a ratio here. I'm going to look at the L2 mu error in the Bochner sense of the difference between psi, which is our learnt operator, and psi dagger, which is the truth. So this is just a typical input and a typical output. But we learn over a measure, and in this case, the measure is a Gaussian random field on the initial condition. And there are many different numerical methods compared here, but I just want you to concentrate on a couple of them. The Fourier neural operator is the best one down here at the bottom. What I'm showing here is the relative error as a function of the resolution used to discretize the partial differential equation. And the take-home message, other than the fact that Fourier neural operator is particularly efficient compared with the others in terms of the size of the error, one thing I would really like you to take away from this is that these methods down at the bottom are all resolution independent. So that is related to the philosophy I was highlighting at the beginning, namely to conceptualize the architecture on function space before discretizing it. And that has the desirable property that once you've learned the architecture, you can in fact transfer it between different levels of resolution and indeed different, even different discretization methods. Here, we're simply showing that at all of these resolutions, we obtain we attain essentially the same error. And that error is related to the finite data set used to train the neural network. If one increases the amount of data, and you'll see this later, these curves shift downwards. You might want to observe this yellow curve here, which is what I call PCA neural network, and I will show you that in the next section of the talk. So here's a quick example with Navier-Stokes equation. This is incompressible Navier-Stokes equation in 2 dimensions with a Reynolds number of around 40. The solutions in this regime are chaotic, not fully developed turbulence, but as you'll see, there is a substantial, there's an energy spectrum as predicted by Kolmogorov, which is present at this level of Reynolds number. Just gives you some idea of what the solution looks like. Here, it's a time-dependent partial differential equation. Here, I'm using PCA, principal components analysis, to illustrate the properties of the equation before I discuss the neural network. So I'm here. So principal components analysis is not used in this neural network, simply to show you how the equation is behaving. What I'm plotting here is the solution of the equation projected onto the 2 highest in terms of energy principal components based on the statistics of the solution over a long time. So what you see here is that there's something which is periodic-like, but there's a regular excursion, so this you can think of as intermittency, away from the periodic orbit, and which is an unstable periodic orbit, in fact. And so in the solution in these blue areas has higher dissipation or in entropy, meaning the H1 norm of the solution is higher in the interior of this disk. Key point that I want to, 2 key points I would like to make here, just concentrating on the left-hand figure for the moment here. What I'm comparing is, what we do in this case is we learn the solution operator over a time interval of length h, and then we use the Markov property to compose that operator with itself to make predictions over long time intervals. So we're learning the solution operator of a time-dependent PDE. We have a choice over what time interval we learn it. Once we've learned it over that interval, we can compose it and make predictions into arbitrarily far into the future. And then you can look at the statistical properties of what you've learned. And the key point here on the left is that we're able to reproduce the Fourier spectrum of the equation itself by means of this neural network, Fourier neural operator. There's some nuances here. So UNet is a comparator, and we're beating it considerably. But even within the Fourier neural operator context, there are issues about whether you train in, for example, L2 or H2. And as you might expect, training in H2, which is a stronger topology, gives rise to a better error. We have more detailed analysis of that question. And then the second point I want to make is that we're obtaining speed up by many orders of magnitude, here at 3 orders of magnitude. That means that if you, for example, and we have tested this, solve Bayesian inverse problems based on the forward solution of the Navier-Stokes equation as part of the parameter to data map, we can solve problems that will be intractable if you had to use the numerical solution of the PDE, because we replace the forward map by the neural operator and use the orders of magnitude speed up to make, in this case, I haven't shown you this, but we do Bayesian inference using that surrogate model computed from the neural operator. Any questions on this? Because I'm going to change to another architecture now. Okay, so the second architecture I want to describe, this is joint work with Kaushik Bhattacharya, who was also involved in the previous work. Bamdad Hosseini, who was a postdoc at Caltech, is now a professor at University of Washington in applied math, and Nick Kavatsky, who was also involved in the previous work. Very simple and natural idea underlies this. Again, we're interested in learning operator psi dagger, which maps X to Y. That's on the left-hand side of this figure. And the approach is to find autoencoders on the input and output space. So autoencoders you can think of as approximate factorizations of the identity, which go through a finite dimensional latent space. So on both X and Y, we have an autoencoder. That's something where the composition of G and F is approximately the identity. But F maps the function space X into finite dimensions, and G maps finite dimensions back into the function space. We do that on the input and output space. That introduces latent finite dimensional spaces. And then we learn a neural network in the latent finite dimensional spaces. And so the objective here is to learn the autoencoders, FG on the 2 spaces X and Y, and to learn the neural network var phi in such a way that the composition here of Fx with var phi and Gy is approximately psi dagger. And this theorem is a statement of the achievability of this. So what this theorem says is that given any epsilon, it's possible to choose the dimensions of the latent spaces, the data volume n, and then a neural network, which will depend on epsilon and the dimensions and on n, finite dimensional neural network, to obtain epsilon accuracy. This is measured in the Bochner norm and averaged over the data. So this is a pretty soft result. We prove it under quite general conditions, initially on psi dagger being Lipschitz, and then psi with initially psi dagger globally Lipschitz, and then locally Lipschitz with some moment conditions. And what is lacking in this theory is a really careful analysis of the complexity of the network as a function of epsilon and the dimensions. And I would like to refer you to Geeta's talk, which is coming later, which gets into these kind of questions about the complexity of the network for model reduction problems of this type in much more detail. But this theorem shows in any case that the method is plausible. And in practice, we find it works. So let me give you a prototypical example. This is what's known as Darcy flow. So this is a problem that arises in subsurface geophysics. And an interesting, it's an elliptic equation for U. And of interest here is, for example, the mapping that takes the coefficient of the partial differential equation A into U. And I'm going to show you some numerical experiments where we work with a probability measure on A, which you should think of as A as being in L infinity, but the probability measure is supported on a separable Banach space. All of this is really appropriate in the separable setting. So the probability measure is supported on a separable Banach space. It creates binary functions of the type you see on the left. These are natural for the physical problem of interest, and the output's on the right. And here I'm showing you the relative test error in the Bochner norm, again, as a function of resolution. So as I showed you before with the Fourier neural architecture, we're obtaining the same level of error at different levels of resolution because of the way we designed the architecture on function space. And then secondly, as I go from green to blue to red, I'm increasing the dimension of the latent space, 20th, 50, 70. And we have a fixed amount of data here. So here you're seeing the advantage of increasing the dimension of the latent space. And I should have said that the autoencoder that we're using in this case is simply PCA. And we found we couldn't beat that for this problem. And that there's reasons why that is the case. All right, just quickly, we've used this problem to do numerically to perform homogenization for a problem in crystal plasticity. I'll just give you some of the structure of this. Plasticity takes the following form. So you have something here that looks like a damped wave equation, nonlinear wave equation for a variable u, but it depends on something called psi. These are known as internal variables, which themselves evolve according to a dynamical system that I'm not showing to you here. This is a microscale material that has slowly varying properties at the small scale with scale epsilon. At a very high level, because I don't have much time, this problem is characterized by what's called the constitutive law that maps the gradient of the deformation u, the internal variables, and the small scale parameter epsilon to the stress. And what we are going to do here is homogenize this problem and obtain a homogenized constitutive law that gets rid of the epsilon and gets rid of what are called the internal variables psi and replaces them with a constitutive law p bar instead of p that depends on the past history of the gradient of the deformation. The key advance here comes from getting rid of epsilon. The fact that we have history dependence on here is not entirely desirable, and our current work is aimed at getting rid of that. But I'll describe what we have done in this context. So we use the PCA neural network that I described on the previous few slides to learn this constitutive model P bar. So that's a function, it's an operator which takes the past history of the deformation into the history of the stress. And what makes this problem challenging is that what I call the probability measure mu is not known to us in this setting because it's implicitly defined by the solution of the problem itself. And so there's an interesting question here about how to design the training measure so that out of distribution it still performs well. And we found experimentally that by training with random strain paths, we learned models that were efficient when used out of distribution in a number of natural physical experiments. These go by the name uniaxial tension and loading and unloading. So there are interesting questions here about training with when you don't know the appropriate distribution. And I think the key point to get across here, as I did with Navier-Stokes equation, is that we're getting orders of magnitude speed up. In comparison with FEM squared, which is the standard fully resolved methodology, we're having a speed up of a factor of 1,000,000. And even compared with what's known as Taylor averaging, which is an ad hoc method that's widely used, we're getting a factor of 1,000. So the method shows great promise for speeding up those problems. Now, I just want to finish, I'm just checking my time. I think I have 4 more minutes. I just want to tell you about a little theory that we are developing to try and understand the relative complexity of learning compact, bounded, and unbounded operators. And this is joint work with Martin de Hoop, who is at Rice, Nick Kavachki, who we've mentioned before. Nick Nelson is also a PhD student at Caltech, and myself. There's a lot of notation to take in here, and I don't expect you to be able to take it in the amount of time that I have left. So let me try and explain to you the highlights. So the problem we're interested in is learning the operator L in the equation that I've highlighted in blue. And the operator L is going to map between Hilbert spaces. We have a Hilbert scale in this setting. And we will look at different cases where L is compact, bounded, and unbounded, and try and understand the relative difficulty of them. We're going to work in a setting where everything is Gaussian. So the input measure will be Gaussian, the noise, eta, will be Gaussian, and that makes this tractable. And in this setting, we're able to fully analyze, in a Bayesian sense, the learnability of L. And I won't go through all the detailed notation here, but anyone who's interested can get the slides from me, or I will give them to the organizers to put on the website. What I would like to, we express this in terms of learning theory, and our key results estimate the, if you like, the minimizer of the empirical risk. Let's just concentrate on this error bound. We study the error in the minimizer of the empirical risk compared with the minimizer of the risk, which in this case is the truth, L hat. So this is the estimated computed from the data. And we get convergence rates, for the most part, we have lower bounds as well. So the convergence rates are sharp. And the rate of convergence alpha is something we're able to quantify and understand in terms of the hardness of the learning problem. So roughly speaking, returning to this, it's harder to learn unbounded operators. So the question we're trying to get a handle on here is whether one should directly learn inverse operators for inverse problems, or whether one should instead learn the forward operator and use that as part of a solution method to compute the inverse operator. So here's a very simple example to finish this section, which is comparing the rate of convergence with respect to n, the amount of data, the rate of convergence shown by the slope, when we learn three different operators, all found from the minus Laplacian, in the case of L being unbounded, the identity, and A inverse, which is compact. And you see what you see here is part of the more general and very precise theory that we have, which quantifies the hardness of learning the inverse operator as compared with the forward operator. Thank you. So I hope I've shown you a general philosophy to this problem. I'll leave these conclusions up there and just say that I think that the philosophy is a good one. I found it very useful in many other areas of applied mathematics. Think of the problem on function space before you discretize. There are many, many theoretical questions that remain open in this area. And one thing I think that's food for thought that I just want to bring up is that neural networks in general, and you'll see this in all of the theory that is developed by everybody in this field, they refer to the existence of a neural network which has certain properties from an approximation theoretic viewpoint, and never prove that we actually find that neural network. And I think that is a substantial barrier to the use of neural networks in a principled fashion. And I did want to just highlight this work with Nick Nelson, where we work with random feature models. These fell out of favor in standard supervised learning, but I believe they might hold a lot of promise in the context of partial differential equations, precisely because I believe they will be much more amenable to theory, which actually relates to the solution that we compute and work with, in comparison with neural networks, where the theory is not usually directly related to the neural network that we find in practice. Okay, thank you. I'm sorry I went over by a minute. Thank you very much.
Thanks, Andrew, for the great talk. There were already a couple questions posted in the chat. So Lanka, do you want to unmute yourself and ask?
Right, I could. I was just wondering about the last part, the exponent alpha that you get. Like,
yes.
What is the value, and is it tight in the sense that it matches if you try numerically to actually evaluate this gap? Do you get that exponent?
Yes, thank you. Really good question. Firstly, I haven't expressed the exponent because as those of you who are familiar with these kind of Bayesian analyses, the exponents are very complicated and they're hard to take in. They depend on the regularity of the input data X, the regularity of the output data Y, the prior measure on the operator L, and so forth. So very complicated, but we do have upper and lower bounds, first of all, in many cases. So the results we have are sharp. And secondly, relating to whether we see the exponent alpha in the numerical experiments, the answer is yes, with enough data. We see them in almost all cases. There are problems where it's quite difficult to see them. You expect n to the minus a half is something you can't beat here. But occasionally, in many cases, alpha will be worse than the n to the minus half rate. But sometimes we just see n to the minus a half because we're not resolved the problem enough. But mostly we are able to resolve it enough and see sharp rates. Thank you. We should finish the paper soon and be happy to make it available over the next month or so.
There is another question in the chat from Frederick Nataf. You want to unmute yourself and ask?
Yes, thank you. Do you hear me?
Yes, I hear you, Frederick.
Okay, good. Well, thank you for your talk. So as for the time-dependent problem, so what you do is you try to infer from the solution at time t, the solution at time t plus delta t, let's say.
Yeah.
So now could it be possible to learn on a finite time interval? For instance, you have some periodic or nearly periodic events, and you want to learn not from one time step to the other, but on a time interval.
Right, I see. So you mean you'd like to learn the entire solution as a function of time? Is that the question? Yes.
Exactly, yes.
Yes. So we have in fact applied the Fourier neural operator approach to that problem. So the one where we map the initial condition into the time-dependent solution over an interval. And it's indeed the methodology and the ways I've been describing it to think about the problem in this talk, they apply in that setting as well.
Okay, thank you.
Thanks.
There was another question from Eric Van den Eyden about speed up. Eric, do you want to ask?
Hi, Andrew. Can you hear me?
Hi, Eric. Yeah, nice to hear your voice.
Hi. Nice talk. Thank you. So I was wondering, I mean, you gave these impressive speed ups, that the method achieved. But if I understand correctly, in order to train the network, you first need to solve the problem by traditional means, get the data, and then use these data to actually optimize the parameters in the network. So when you talk about speed up, are you taking into account this initial phase or no?
No, that's a good question. So I'm doing something that's common in, for example, reduced basis methods, which is to think of the training as a cost which is amortized and you can ignore it, and simply reporting the cost without the training. So it's the evaluation cost. And your question is a really good one, because it points to something else that's different in this area of surrogate modeling from standard neural networks, which is that we actually have choice of the design measure mu, and the design measure mu should be chosen or can be chosen in relation to the problem that you want to solve. So for example, if you're trying to solve a Bayesian inverse problem or a design optimization problem, you may well be able to learn something about an appropriate choice for the measure mu a priori by cheaper computational methods. So for example, we've had success in climate modeling using ensemble methods to locate the regions of parameter space where we want to be focused, and then to do the learning with a probability measure that's centered near to those places. So I think there's a lot to be done here in terms of choosing the measure mu and the training phase in a way that's adapted to the surrogate modeling that you might want to do later on. Thanks.
Yeah, I see. I mean, I guess to the type of question you want to ask, because for example, in the case of climates, if you are interested, in extreme events or things like that, the way you will gather the data, it needs to be tailored to that. Otherwise, the generalization in this part will be difficult. Right?
Exactly. Yeah. So that the measure, one could also use this method for scientific discovery, in which case you don't have control over the measure mu. But if you're using it, if you're using the problem as a surrogate model, then the choice of the measure mu and its relation to the problem you want to solve later is absolutely crucial. And that's an area where I think there's a lot of interesting open methodological and theoretical research needed.
Okay. Right. So maybe just one last thing. At the beginning of the talk, you alluded to the case where the input dimension would be large as well. But in that case, the data acquisition would be much more complicated, because how would you solve the problem to begin with to get the data?
Yeah, I agree with you. So that's a problem for the future, and perhaps maybe, there's been, as you know, some very interesting advances in that area, but with Weinan's work, Jensen, Ji-Chun Han, combining some of those ideas with what I describe here might be the way to go.
Okay, thank you.
Thanks, Eric.
Okay, thanks, Andrew, for the very nice talk and for discussion.
Thank you.
So I think let's take a 1-minute break and before the next talk. Sid, are you there?
Yes,
Oh, yes.
very much. Shall I start by sharing my screen then?
You try.